This is an example where we're modeling a tubular reactor as a laminar flow reactor. And we're going to use a segregated flow model, which means we're going to treat the laminar flow reactor as a bunch of plug flow reactors in parallel, where the length of the plug flow reactors is determined by the velocity profile in laminar flow. So we have a second order reaction. We're given the rate constant, isothermal reactor, and we're given feed concentrations and feed volumetric flow rates. And the question is, what is the conversion in this laminar flow reactor for a volume of 1,500 liters? So first, let's look at what the velocity profile is that we're talking about and how we're going to model this. So this is just an approximation of the velocity distribution. The velocity in the center is twice the average velocity, and of course the velocity goes to zero at the walls. And so from this velocity distribution, it's possible to derive a residence time distribution. This is not a straightforward derivation. It takes a little bit of work, and so what we want to do is use that residence time distribution. And we're not going to derive it, so the residence time distribution, and I'll use the symbol P of t, so it's function of time. The residence time distribution is 0 for time less than the space-time over 2. So the space-time, the average of this distribution of velocities, is the space-time, the volume of the reactor divided by the volumetric flow rate. And the center section of the reactor, of the tube, arrives if we did a pulse tracer experiment to get the residence time distribution. That center arrives first at half of the space-time, and the residence time then is equal to space-time squared over 2 time cubed for all t's greater than or equal to tau over 2. And we can plot what this looks like to give a little better feeling for the behavior. So here's the residence time distribution plotted as a function of time, 0 up until tau over 2, and then this delay is t to the minus 3. And so the idea of segregated flow is that we can calculate the average concentration of a reactant leaving the reactor, and I'll use this symbol to indicate average, by integrating over all of these plug flow reactors in parallel. So integrating from 0 to infinity, P of t, the residence time distribution, determines the different types of plug flow reactors and their residence time we would have. And then the concentration changes with time, and this is essentially a batch reactor. And so if we use this model, the concentration we get here is the concentration at the exit. And we're using the residence time distribution, and the concentration is a function of time from a batch reactor. We can make this a little easier to do the calculation by just differentiating this equation. And then we're going to solve this differential equation, where, of course, initial conditions are going to be at time equals 0, Ca bar equals 0. If we go back to this equation, if we integrate only to time 0, then the concentration Ca average is 0. And then we need the batch reactor equation for the concentration, and it's second order, minus sign, concentration of A, second power. We also need initial conditions for this, and that's that Ca is equal to 12, and this is given in our problem statement, 12 moles per liter. Then, of course, have to solve also in these equations. We have to have P of t. This is the format that I would use in Polymath. So if t is greater than tau over 2, then P of t is tau squared over 2t cubed. Otherwise, it's 0. So we have three equations. We have the initial conditions. We have to put in values for k and for tau. So k is given. Tau is the volume over the volumetric flow rate. So tau is 3 hours. And then we need to integrate this initial value problem, two differential equations. What we're going to do is integrate from time equals 0 to some long time. And turns out that 20 hours is more than long enough to get sufficiently accurate answer. We can show this by integrating to different times. And if we use Polymath, and I'll show you what the Polymath program looks like, we can get Ca leaving the laminar flow reactor 1.13 moles per liter. The problem asks for conversion. Because it's liquid phase, we can write conversion in terms of concentration. So the feed concentration, exit concentration over the feed concentration, conversion 0.906, or in significant figures, 91% conversion in this laminar flow reactor. And let's look at the Polymath program. So the Polymath program has differential equation, initial condition, the batch reactor differential equation, initial condition, the constants. We integrate it to 20 hours. Also did integration 10 hours, and within three significant figures, the same answer. And then this program calculated the conversion. And so this is a different conversion than we get for a plug flow reactor by taking into account this velocity distribution.